For the introduction. I'm Yaron. I'm a co-founder and CTO for Iguazio, a company focused on machine learning operations and automating the creation of production pipelines for machine learning. I'm going to speak today about what is MLOps and a few other terms in that space, and especially how to accelerate the deployment of AI and machine learning into production. We all know that one of the main challenges in machine learning is not just building it into research, but also deploying a real application, real business application that generate real value. And this is what we're going to speak about today: is how to drive, how to enable those production applications that use machine learning and AI, and how to do it extremely efficient and simple. So the agenda for this session, which is going to be slightly long, is those items that you can see here. First, the challenges when productizing AI and machine learning. Then understand the concepts of what is the MLOps and feature store and things like that that are part of building a solution for operationalizing machine learning in a simpler way. We'll go over the 3 stages in building AI and ML applications and sort of how you need to structure your project. We'll go into MLRun, which is an open source project where we support that does MLOps orchestration and feature store and a few of the other pieces that we're speaking about from A to Z. As we talk about the details, we'll also show 2 demos. One is how to develop models and track and experiments and build pipelines and so on for development. And the second demo is sort of the more advanced demo of how to build like real-time operational pipelines that are sort of more automated, more advanced for real business applications. So we'll show those 2 demos, and without further ado, let's start. So the first problem that we're going to tackle as we operationalize machine learning is that the research environment today in most organizations is very different than the production pipeline, which incorporates AI and ML as part of the pipeline. So in the research environment, the way that you usually work, you take some CSV extractions from some data, from historical data or operational data, and you run some exploration using different tools like Pandas, Jupyter, and so on. Then you sort of do small-scale training within your notebook or using some cloud service and evaluate the results, charts and all that, and reiterate, change parameters, change the data until you have sort of a great model, and then you deploy that model as an endpoint. But in reality, the world is pretty different. It doesn't work with sample data from a CSV unless all you want to do in life is build some reports, predictive reports. If you want to build a real application that incorporates machine learning and AI, you have to follow sort of the right model, the model on the right. So essentially feed data from operational databases and data sources using ETL, do streaming, feed data from Kafka and logs and so on, integrate with a variety of APIs that enrich the data with more information. You need to get all of that data, which could be massive, and prepare that at scale. Running a data analytics job on a notebook probably won't cut it for you. So we may need different analytics tools and batch technologies. Finally, as we create the data set for training, which may be larger now, we need sort of distributed training. We need to be able to train the model at scale across a lot of data, but also potentially with different permutations, trying out different models, different algorithms, different parameter sets, hyperparameters, and so on. And that's not something you want to do on your notebook. That's something you want to do on a cluster or sort of on a managed service. So once you do the training at scale, you have a model, and that model needs to be served either as an HTTP endpoint, which is the trivial use case, but in many cases, it's actually listening on a stream like a Kafka or something like that. The model needs to auto-scale to be able to address different demands, need to fail, gracefully, fail over gracefully, or you need to be able to upgrade the models and do A/B testing and things that really real production would need, and not just like creating an endpoint which is good for very basic scenarios. Now, as you build the model, you also have to monitor the model behavior to identify problems around drift and potentially model inaccuracy. And you need that model to also be integrated with APIs, because in most cases, you'll have some front-end application or a dashboard or an application that sees some activity and then triggers an event and so on. So we need also integration with the API. And one of the big challenges is also in the model serving part to have access to the data, because the data that you access in the sort of the serving part needs to be sort of low latency, be able to address high concurrency, high number of requests per second, because we usually need to satisfy applications with users that may throw thousands of requests per second. So usually the way that this is done is in many organizations is called throw over the wall. Someone builds the model, builds a nice Jupyter, someone takes that thing and redevelop the entire thing, whether it's in Java, in C, or even in Python, but design it more as a containerized workload and so on. And every time you need to make some change, you reiterate for that entire process, and that's very tedious. And so, if any of you thought that you could just take a Jupyter notebook and make it run in production, so I have news for you, that doesn't really work. What we really need to do is take those pieces of code that are developed by data scientists or data engineers and refactor and operationalize them into something which is more of a managed service, elastic, managed, monitor, secure, and so on. And that possesses a lot of challenges. So if we need to summarize, what are the challenges when you operationalize machine learning? There are a lot of different challenges in machine learning, but the ones that focus on operationalizing your work are those 4 categories that we've seen with most of our users. So the first one is about siloed work. We spoke about the fact that data scientists may work on their Jupyter and their sort of tool set. They're not really designed to work on, they write code. They don't try to think about exception handling, error handling, security aspects, and so on. You have data engineers. Many use things like Spark and Java and different set of tools. DevOps and ML engineering will usually use containerized workloads, Kubernetes. So there's no single ecosystem where they can all collaborate, and you have those silos. The other thing is that when you build things to production, it's a very, very long process. We're going to look into what it means, but you need to write the code, but that's not enough. You need to package and scale and secure and monitor and test and so on. That's a lot of effort for many people, which go beyond the data scientist role. One critical aspect that we see across the board, you develop some model based on some test data. Someone created some CSV files. It took him potentially months to get approvals, to get data from different places and anonymize it, and so on. And now you're doing the training. Now you go to production, you don't have the same data. You don't know where to bring it from, or there are political reasons why you can't access it, or maybe you don't have security credentials to access that data, or maybe the access to the data is so slow that you can't really incorporate it in a production pipeline. There are many reasons why eventually you'll see that people use less features, which impact the accuracy, or misuse of feature that also may impact your accuracy of your model. And talking about accuracy, it's very important in production to track the accuracy, be able to see when it goes down, when you have drift in the data or the model, and remediate. Remediate means like retrain with fresh data, exchange the models with an ensemble, all sorts of remediation techniques to make sure that you're accurate and you're not creating any liability for your organization. So just to understand, why is it so difficult to take something to production? So if you build a piece of code in your notebook or PyCharm, it's not the end game. What you really need to do is build it in a way that it can actually run on a cluster in a resilient way, and that means packaging your code, putting it in containers, building it, scripting, and so on, doing unit testing. Then you need to be able to scale, because in many cases the data may span across, or maybe large enough that you need to be able to distribute it across multiple computation elements, or maybe partition the data, or maybe distribute the model to smaller pieces that can run on multiple CPUs, and so on. Then as you go into production, you find that maybe the code that you did, which worked great for some experiments, is not so great for production. It's too slow. You need to serve like 1,000 requests per second, but you can only do 1 or 2 requests per second the way that you built it. So then people need to build parallelism, asynchronous design, add GPUs for acceleration, tune the queries, add caching, and all those techniques, which are really more performance engineering. They're not the practices of a traditional data scientist or even data engineer in some cases. And also, if you want to drive things into production, everything in production must be versioned, secure, logged, monitored, and so on. So you can track failures and debug them. You can avoid, SLA problems. You can avoid security breaches, and everything that you do must be automated, because we're not about delivering something one-off. Because we may change the model, we may change the data. So everything needs to be continuous, or in a CI/CD form like modern software techniques. So we need workflows that when we change a bit and we want to recreate the models or recreate the data engineering components, we can just do that based on an event or a click, and not do the entire ritual as a manual process. Now, as you can see, the majority of the effort today is not really developing the piece of code that trains the model. The majority of the effort today is driving it into production. This is where you'll see that some organizations spend almost a year in building an application. An application is beyond the model. It could consist of also the data engineering part, the data preparation part, the integration with APIs, and so on. And for some organization, again, it could take a year, where the data science work may take a few weeks. So that's an important note. We have some nice case study with one of our customers, Ecolab, that shows how they moved from a year to production on a single project to delivering 4 projects in a few months by just applying all this sort of concept of automation and MLOps. So why is it so complicated? It's also because we do a lot of different things in order to run to production. We have different implementations for the research pipeline, for the deployment pipeline, and for the governance. So that means people, that means more labor and more time. So in the research pipeline, usually we throw all the data into a data lake. We do different batch transformation using pandas or SQL tools. We create some sort of a subset or enriched data set or training set that could be fed into the training. And this is how we're doing the training. If we want to scale the training, there's also like ML engineers that take the piece of code that was done on Jupyter or on small scale, and they convert it to something that can run as a job, containerized, and so on a cluster or in an automated CI fashion. So it could be repetitive and scalable. Now, this is only the first part. As we go into the operationalization or the real pipeline, we need to build a new pipeline which has different building blocks and different technologies. So it may need to attach to operational databases, your Oracle, your Teradata, your cloud databases, and so on. Streaming data coming from Kafka, Kinesis, and so on. Integration with APIs. Some data may need to be fetched from some service that provides information about a user or other things, Facebook, Twitter, etc. We need to gather all of those different data points in real time or online and transform them into something sort of that is aggregated and joined and so on, to turn them into meaningful features that will reside in an interactive database. Because as we do the serving, we don't want to run large queries every time a user logs into the site and we need to provide a recommendation. So we need to have some sort of an online DB, usually NoSQL for scale and performance, and then the model is being served based on the data that's stored in those NoSQL databases. And again, we didn't really finish the process, because now we also need to monitor all the activities, everything that goes in and out to the model, all the feature vectors, all the data, all the telemetry, performance, latency, and so on, must be monitored so we can track failures, we can track accuracy problem, we can track drift problem, we can explain the results if someone is sort of suing us why our model is misbehaving, so we can go back and see what really happened. So everything needs to be monitored and logged, and this data needs to be available for further analytics like explainability algorithms, accuracy analysis algorithms, and so on. And this data may actually be used for retraining our model in production. So again, we need to figure out how to do automated training pipelines that are triggered by some event and fresh data, and build a new model and reload that model while the system is actually running. So there's tons of work and tons of challenges. We build different pipelines by different people. It means more labor and also inconsistency in the implementation, accuracy gaps, very slow processes. This is really why it's going to take you so long to build those solutions. So the new approach that is now becoming more and more dominant is to use the concept of MLOps and automation, along with something called the feature store. Feature store is sort of an automated way. Most of the problems in machine learning are really about creating the data for production and for training. So feature store is really about automating all of that. It's providing a cataloging system for the features for online and offline. Essentially, the same feature have different implementations for online and offline, but it needs to be accurate. So same statistical behavior and data behavior and so on. And the feature store, a good feature store, also have an automated transformation pipeline, which is sort of an automated machine to get some sort of a recipe and generate the features automatically. You don't want to build the features again and again manually, and for the different three areas, the research, the deployment, and the governance, you want to have a single system that generates the features for those three applications. And then usually those applications, the training, the serving, the model monitoring, the governance, are sort of microservices that rally around the feature store and add, and essentially our applications usually are scalable, and you can just fetch data from the feature store, run something, and store it back. So this is the general concept of sort of MLOps and the feature store. Now let's talk about what are the 3 steps that we need to go through when we build a machine learning product. Okay, so the first, as we mentioned, is about data collection and data preparation. What does it mean? That means that we have different sources, and later on we're going to see some demos of how this is really achieved in a real application. So we have different sources. Let's assume we want to do fraud detection. So we need to collect transaction data, we need to have account data, activity data, and so on. All those different data points need to feed into some system. That system needs to start manipulating it, making it meaningful for machine learning, like aggregate by time, like hourly stats or weekly and amount of transactions and so on. It may need to be joined with other data because for example, I have a zip code, but the zip code can give me information about the social economic situation in that specific region in the country. So I need to join the data between those 2 tables and get some meaningful data which tells me this customer lives in a fancy neighborhood. Okay, and this is just an example, and there are many such examples. There are also machine learning transformations like one-hot encoding, imputing, etc. So once we have those features, we need to have those features serving 3 different applications. The first application is building training, which is usually done in a batch way. Then we have serving, sometimes in batch, but in most cases in a more interactive and real-time fashion. And also the governance part needs to essentially compare the real behavior of the features in production with the expected behavior. And the expected behavior is essentially stored with the features themselves. The features have metadata, which tells us their histograms, their statistics, and so on. This is really how we can compare in production, see, are we behaving the same way we expect our model will behave? And if not, then we have a problem and we need to deal with it. Okay, so the first thing is about how to collect and prepare data. And later on, we'll see how it's going to be implemented in a production way. The second part is creating a model development pipeline. What does it mean, a model development pipeline? That's usually what the data scientists do, but we need to think about how to do it in a more iterative, scalable, an automated way. So usually you take a piece of data and you run exploratory data analysis. You take notebooks or other tools that show you different information about the data, and then you choose the features. You can run automated feature selection, which is also another mechanism. Let's assume you have 1,000 features. You don't want to train on 1,000 features or 100 features. You may want to run some algorithms that will reduce the amount of features and understand the importances, and only those features that get selected will feed into the real training. Once we do the training, we also want to evaluate and test our model. So evaluate and test means that first make sure that it's accurate and so on, but also make sure that it's correct and it doesn't fail and it performs in a decent way and so on. And now, as long as we don't get to the goal that we wanted to achieve, we go back to square one. We may add data, we may change algorithms, we may change parameters until we get the right model. So that's the second phase in machine learning. And finally, once we have a model, then we need to think about how to deploy that model into a real application. So usually, a machine learning application has some events or requests or triggers that will trigger some sort of activity, and that will be intercepted by an API. So we need to build some API that gets, for example, a user ID or a request. That user ID may need to be enriched with information about that user, his recent activity, his account balance, his gender, and so on. And then that enriched data need to go into a served model that is serving our algorithm. But in many cases, we may actually have multiple models to serve together, and that's something called ensembles or multi-arm bandits, etc. And why is that? Because, for example, let's assume we train data on the last week or last month, and we also have a trained data on the year or a season. So we know we may want to incorporate into our results in things that are more temporal decisions, more recent, and things that are more long-term models. Take COVID as an example. If you take a long-term model and try to learn based on that model, then maybe buying patterns change and things like that. But on the other hand, if you compare with a model that was trained on the last week data, then you'll get something which is more accurate. So in some cases, we create combinations of models, and sometimes we even combine models that are deep learning with machine learning to create some sort of enriched feature set. And once we have the response of the model, we need to respond to the user, either directly to the request of the user, or push the results through a stream into some other application that will do something with it. But in the same time, all of our results need to go into a monitoring framework that sees the request, sees the results, and based on that, analyze if we have drift problems or inaccuracy problems, and so on. So this is how the operational pipeline would look like. And there's one big challenge with all of that is that if I need to build all those things today, there's a huge stack of tools that I need to manually go and integrate and sort of make sure they all work together, they have the same authentication, the same users, the same logging, and so on. And that's a huge effort for IT. So one of the things that we've created as an open source project is a mechanism to orchestrate all of those things through a layered and very modular approach that allow us to add more and more component as we go. And I'll show that in a second how it actually works. So the different layers in the solution, first is the concept of a feature store and data store and artifact store. This is where all the objects in the system are stored or referred to. And we're going to see in a minute what does it mean a feature store. So all those features then later on will be used across the pipeline. The second thing that is very important, we talked about the effort of taking a piece of code and making it something that runs at scale in production, secure, logged, monitored, auto-scaling, can do rolling upgrades, all of that. That's a big chunk of work for DevOps and ML engineering. And the way to eliminate that is by using serverless technologies. And we'll explain what it means, but essentially you can throw in a piece of code and there's a lot of automation that builds a service from your piece of code. And all the things that we discussed before that take so much time are essentially being automated. And we can also take a piece of code and store it as an artifact in a marketplace and reuse it later for our pipelines. And there's also in MLRun, by the way, you can just go to mlrun.org or MLRun in GitHub, and you'll see more details. It has specific code for the different aspects of the stack, sort of the feature engineering, data preparation, the model training automation, the real-time pipelines, the data and model monitoring. And the nice thing about it is all glueless. You don't need, like, if you're going to take one framework for model serving, another framework for model monitoring, another framework for feature store, another framework for training, you end up doing a lot of glue logic yourself. Here it's all glueless, and we're going to see that in the demo. You can just pass objects from one tier to the other. And what is the philosophy behind it is, again, we want to kill the silos. We don't want people to work in different silos and manually pass things from one step to the other as it evolves towards production. We want to essentially be able, that people will run in their native environment, within their native Jupyter notebook or PyCharm or VS Code or any other IDE tool. We want them to install a very simple SDK locally, which allows them to track what they're doing and prepare it to production automatically, essentially. And then the minute that they want to run it in a bigger scale, they just click one button or call one command, and it will run on a cluster. Because again, they might want to process more data or use GPUs or resources that they don't have at their disposal on their IDE. So again, single command, it will run on the cluster. Once we feel that whatever we're running, whether it's a training job or a data preparation job, is great, we can just take that job and plug it into a pipeline. And we're going to see in a minute how we do it. We can just plug it into a pipeline, run the entire pipeline, whether it's on a trigger, in a CI system, in a manual way, and so on. And because those functions that we're going to use here are auto tracking, so they know how to track their behavior, their resources, etc. So you're getting all the tracking for experiments, for CPUs, for GPUs, for everything. You're getting that for free without adding too much code. Now everything is reusable, so we can store pieces, we can store workflows, we can store object functions, features, and so on, and reuse them within the same project or even for other projects, and that saves a huge amount of work. So that's just to understand the philosophy about sort of more continuous development, continuous integration in machine learning versus more sort of a siloed approach. So why are those functions are really great and useful? So the general idea is that you provide a piece of code, and there's a lot of automation that turns it into a fully managed service that runs on Kubernetes clusters with storage, with telemetry, with logging, and so on. Also, part of the design of those functions, you know, in some cases, things like Amazon Lambda functions, they actually slow you down. They're slower than your own implementation. In those frameworks that we support, Nuclear, MLRun, etc., it's actually the other way around. Because there's parallelism and real-time engines built into the serving runtime, the serverless runtimes, it actually accelerates your performance compared to just running it locally. It accelerates it, it scales it out. You can also see it essentially knows how to run many different workloads horizontally scalable. So deep learning, machine learning, analytics can now scale horizontally across multiple virtual machines without you doing anything. In some cases, just adding a single line of code to attach to the clustering mechanism. And also, this is all can be reusable. You can just create a function, store it in a marketplace, and drag it later on into your pipeline and use it. So that, again, maybe the first project you work slightly more, the next project you're just going to reuse what you've done in the previous project. We spoke a little about the concept of auto tracking and managed execution. The general idea is that usually you have your piece of code. What we do, we wrap your code with an elastic runtime, and there's about 7 different such runtimes: Spark, Dask, Nuclear, Horwood, and so on, depending on the workload. Like some are for deep learning, some for analytics. And everything that goes in and out to that function is, think of it as sort of as a sandbox, that sort of auto flight recorder. So it knows how to push into your job. It knows how to push data through pointers, secret credentials, parameters, and so on. And it automatically tracks everything that's generated by that job, whether it's data artifacts and logs and telemetry data and results and so on. And this can also be plugged gluelessly into a pipeline. There are a few pipelines that we support. Kubeflow is one of them, but also others. So that really turns your code into sort of something which is managed, auto-scaling, resilient, and fully tracked. So if you see, these are, by the way, some of the screenshots of MLRun. Again, it's open source. So you can essentially, when you define function, you can define scaling factors and resources, GPUs, CPUs, auto-scaling policies, and so on. Usually you don't need to, it's pretty automated. Every time you run something, you get the tracking and all the versions and of all the executions and all the data was generated and lineage information, etc. And you can even zoom into a specific job and get all the details. And as jobs are running in the cluster, you can actually go and see how those jobs progress. Now, the nice thing about it is there's no DevOps, there's no ML engineering. This is all done automatically for you, just the fact that you're running a job using that sort of ML run wrapping capabilities. And the last thing before we go into the demo is we don't just want to run a single task, like a training task or a data preparation task. In most cases, we create a pipeline that may grab data, run some training, run some testing, maybe evaluate multiple models, etc. So we need to be able to build pipelines, and we also want to have those pipelines be automated. So every time we want to do retraining or data gap refresh, or maybe periodically every couple of days, we want to be able the models again. So we just want to define those pipelines and run them automatically. And this is a nice snapshot I'm going to show that we can also incorporate that into our CI system, like GitHub Actions or GitLab CI/CD or Jenkins and so on, with native integration, that every time we update a piece of code, everything gets tracked and everything gets authored and sort of so you can even go back and review what this code change did for your accuracy in your native Git user interface. Okay, so that's and that's with that. So let me go into the first demo. Okay, so what I want to show, we have as part of the MLRun, if you go to MLRun website, mlrun.org, and go to documents, you'll see a bunch of tutorials and examples. The auto guide has some pretty nice example that shows how to take the classic New York taxi Kaggle project and turn the New York taxi Kaggle project into a fully operational pipeline. Okay, so if anyone wants to go to that Kaggle notebook, original one, you can just go through that link. And I'm going to show you how I'm taking that New York taxi Kaggle project and turning it into a fully operational machine learning pipeline. So this is an example for a notebook. Let's see if I can zoom further. Okay, so I may just need to install a couple of packages. And we're setting our environment with sort of a project name. So later on, as we go into our project, we can see everything that we're doing is going to be tracked. So we just need to set up the environment to point it to the project. Now this New York Taxi project has all this sort of Python code divided to different functions of data preparation and training and prediction and so on. This is all the original code. Haven't touched it. Maybe we just cleaned it up a little and put certain pieces of code in functions instead of like straight cells. But essentially, it's the same piece of code that we had in the notebook. The only thing that we've added is sort of something called the context object into some of those functions. And we can use that context object for, it's optional, you don't have to, but in order to log data, log models, and those models or data objects will be tracked automatically in the system. You can also use the context object to grab secret credentials in a secure way and do other interesting things. This is all documented. And if you go to MLRun to concept of functions and jobs, and you can see all the details about how to create the functions, what's a context object, run object, and so on. So Going back to here, so I have different functions. I have like the transformation functions. I have the training function, and so on. So this is the code. One of the things that we did here is we just marked the code with encode, so we know to separate between like the automation part and the actual notebook code. And in here, we're going to execute the code that we have in the notebook in an automated fashion. So the first thing we do is we just take some reference data that's stored in S3, and we're going to convert our notebook into a function. We're going to call it taxi, and we're just going to create a function from our notebook. You see, simple line of code. We can tell it, you know what, it's going to use a certain Docker image as a baseline. It may have few additional packages that are needed for that function, and so on. So next thing that we want to do, we want to run that function and test it locally. We don't want to run it on the cluster. We want to see first that it works, debug, put breakpoints, and all of that. So we're going to run, and we're going to run the fetch data function in our notebook. And you see that it's essentially going to track everything that happened automatically. It's still running in the notebook, but if I'm going to go into the project screen, I'm going to the fetch data job, I can see all the job information. I can see what was used as input data, what were the artifacts that were generated by the job, what were the results, logs. When it's running, you can see sort of the Kubernetes pod information and so on. So a single line of code, and I'm running this with full experiment tracking and so on. And I can see the outputs that were generated. The outputs are special objects. They're versioned. You can see they're a versioned object that could be passed along the pipeline. The next thing that we want to do is run it on the cluster. For running it on the cluster, we may want to have like a shared file system, and we also need to deploy the containers, because remember, we wanted some extra packages to be installed into that function. So we do need to do something called deploy, which is essentially think of it serve as a Docker build, and it adds all those packages that we wanted. If you don't have packages, we'll just skip. But since we did ask for additional packages to be deployed into our job, we push deploy, and then it's sort of ready for use with all of the extra packages that we wanted. And now we want to run it. The only difference here is that here I had local equal true, which is essentially saying run it locally, don't run it on the cluster. And now I'm just running the same without local equal true. And if you're familiar with Kubernetes, and so you can actually see that it was allocating a pod. The pod is essentially launching a container on the cluster and running it, and we can see, what were generated, out of that job, and you can see that we can even access the objects that were generated by that job. The next thing that we want to do is do the transformation function, which takes the data and transform it to our feature vector. So here again, we run the transformation function. We give it some input, which is the output of the previous step. So the nice thing, you can refer to data as pointers, and because data is being persisted on the back end and is sort of creating a link, you can just pass those links between the job. You don't really pass the data, you just pass the pointer to that version of data. And I can see, again, the results from that step, and so on. And you see I have some outputs. Now that I want to train the model, again, I could give it some outputs, give it some input data, and run the job, and I could see all of the results. Now, as I'm running this in the notebook, and it may run on the cluster, I can just go into each one of those jobs or individual versions of that job and see what's going on. So you see the input for that job was this data with this version. The artifact that were generated are a model, and there were some logs for that job. So again, everything I'm doing is automatically tracked in the system. At a certain point, I want to go and serve the model. So now we have real-time functions, because the functions have different engines. We have real-time engines, batch engines, and so on. So this time we create a new function. We create a new serving function from a notebook, and we just add a model into that serving function, and we deploy. This is essentially deploying a real-time HTTP endpoint. You see, when it finishes deploying, it's generating the HTTP endpoint that is going to accept data from our request and respond to it. And when I'm doing this invoke, I can actually test against this real-time function. If you go into this project that we've talked about, you see all those batch functions with their runs, but we can also see the real-time functions. So this is like the real-time serving function with its code, configuration, auto scaling. You can put canary deployments, all that into that function. You can make this function trigger on a stream. If you want to listen on Kafka, just put your Kafka credentials, and that serving function will listen on Kafka with sort of zero work. But everything you can do from the UI, you can do from the API. So if I want Kafka from the API, I will just say with Kafka or with stream with some parameters, and it will add the trigger, sort of the source of Kafka with auto scaling and load balancing and all that built into it. Okay. So that's the gem right here. So I did serving, I did the training, I did data preparation, I did serving, everything in essentially a single notebook, and everything is ready for production because all those functions are now essentially in my project. So all those things can now be used in pipelines, or they're essentially become object in the system. Okay, also my models, my features, everything is becoming an object. I could schedule the work instead of doing it interactively, so on. So now let's build a pipeline. So in this case, we're using a pipeline engine called Kubeflow Pipelines. It's part of the Kubeflow project. In a minute, I'm going to show the same with the CI tool. But I can just go and build a pipeline which is comprised of my function. Remember, I built the taxi function with few handlers, the fetching, the transformation, and training. So I can just create a pipeline that says, go do ingest. I can do the build, adding, the packages to the container. First step, ingesting the data as a second step, doing transformation as a third step, running the training as a fourth step, and finally deploying them all into an endpoint as another step of the pipeline. And I can just execute that pipeline with some parameters. As I do that, essentially, this is going to trigger a pipeline. It's already executed. I didn't want to spend the time on waiting for the pipeline. So I can just go and see the entire pipeline deployed. So the first one is building the containers and then fetching the data, transforming, training, and running the model serving. There are way more complicated pipelines, usually in production, because you also do different testing phases, and you may bring data from different sources. So pipelines may get pretty convoluted in reality. But you can see that I can reuse objects. I can essentially go and work with function objects that I created from my notebooks, and then it's already operationalized. It's already ready for production. If I want to be slightly more sophisticated, let's assume I'm working within GitHub Actions or GitLab CI or Jenkins or some sort of automated CI/CD framework. I can use the same language that we've seen to build sort of a script that takes, in this case, here's creating data preparation, running training, testing, deployment. This one is slightly more sophisticated. It's doing test deploy, so it deploys the model into an endpoint, runs some testing against it, and then sort of verify that it's all working. So I don't need to write the code because the code was already written and exported as functions, or is actually sitting inside my Git repository. So I can just register this CI script, which defines my pipeline in the CI system. And every time I'm making some commit to my code, I'm doing some changes to the data, I can let the CI system automatically run the full machine learning pipeline and generate the model along with all the information about that model execution. So I can, this way, in the pull request as I'm triggering my job, because I changed some piece of code or data, it's automatically running this CI pipeline and reporting into my CI system all the results. So if I want to go later and see this piece, this change in the code, what was the result, I can just go and see all the results. And if I click on the hyperlink, it will open in the MLRun UI. Okay. So again, this is a way for you to start from, you see, from within a notebook. We converted the notebook into managed microservices with telemetry, with logging, with auto scaling, and all of that. We can create an automated pipeline in different ways, whether it's using our native CI systems or using Kubeflow, which is like more powerful. And this is the way to develop models in a more iterative way. Now, next thing we could do, by the way, with those pipelines is the minute we see that we need to train the model because something changed in the accuracy, we can again trigger those pipelines relatively easy. Okay, so with that, let's go back into the next part. Now let's get slightly more sophisticated with the way that we're working. So, because again, if we want to build real production pipelines that listen on real-time data and are sort of tracked and monitored and all of that, we need to start more sophistication. But the nice thing is that the sophistication is not on you, it's essentially on us. You just need to use a few more options in the API and you're going to get something way more sophisticated. So the first thing that really helps you build, because you know, we've seen until now training that, so we built some training data using very naive ways, you know, taking pandas, reading it from a CSV. But what happens if we need to attach to operational data systems like databases, triggers, HTTP, and streaming, etc.? So we need to create data preparation pipelines that know how to directly attach to the operational data sources and build the data for training and for surveying and for governance. Okay? And this is really what the feature store element within the MLRun project is all about. Is you can define pipelines, and we're going to see in a minute how we do it through the SDK. But you can define very sophisticated pipelines of data analytics, aggregations, machine learning tasks like imputing and encoding and so on, and then persist the data into multiple forms. Once you run those pipelines, they automatically generate all the statistical envelope for every feature. There's a lot of metadata per feature. You can put validation rules, etc. So this is the ingestion part. As you create features in the catalog, you can just have someone build a new project, select from the catalog the features he wants to use, and then create a feature vector and use that feature vector, whether it's for training, you know, with those 2 lines of code, or for real-time serving in those 2 lines of code. And in a minute, we're going to see a full demo of a real application using that script. Before, we focused on batch pipelines, like, you know, preparing data, running training, running evaluation, doing some testing and deployments, and so on. But in production, we have real-time pipelines. Again, pipelines that may listen on an HTTP trigger, listen on a Kafka stream, and they need to do all sorts of data transformations and preparations, and maybe run multiple models in a graph, and finally do some post-processing. So this is usually a matter of months of work of many people, data engineers that focus on, that are sort of have the skills in performance engineering and in, you know, data partitioning, all those, you know, very sophisticated technologies. In many cases use Spark or Flink, which are really built for Java users, not really for Python users. So within MLRun, there is something called serving graphs. They're used across the board in different places, also as part of the feature store internals. But you can also use them for building real-time pipelines. So let's assume I need to build a pipeline that has event coming from, say, HTTP, gets enriched, pre-processed, running into an ensemble of 3 models and then doing post-processing. Instead of spending 3 months, you can do it in about a day. You can just create such a pipeline in Python, with native Python code, and you can, within your notebook, you can test that pipeline, see that it responds based the way you want it to respond. If it's okay, you just say deploy, and that's it. You have a full running operational pipeline, runs in real time, auto scaling, listens on streams or other types of data sources, all fully automated. The other aspect of that is that it's not just dealing with the data, it's also dealing with the telemetry in an automated way, and drift analysis and accuracy measurements and data validation policies. All of that is fully automated. And the way that it works is that once you deploy this graph, this pipeline into production, and it's running on those RealTime Nuclear functions. Nuclear is an open source project, very popular, that does real-time serverless implementation, very high performance. So essentially, the way that we do it, we deploy the functions, and we deploy the Python code into those Nuclear real-time runtimes. So this is how it scales and performs. So those serving functions, essentially what they do, they grab data from the feature store every time a request arrives. They essentially join the data from the request with the data we have on that user from the feature store. And they may also grab things like validation policies and statistic policies, etc. Once they do the prediction, they also write back into a streaming engine. They write all the requests, the predictions, the latency, the performance, all of the telemetry that's associated with that request and response. So, and you have other functions. Now, you don't need to do anything in order to get this to work. You just need to turn tracking on your model, and that will all happen automatically. Those other stream processing functions, what they do, they grab the data from real time. They do real-time analysis on the data to understand the statistical behavior of the features of the model. They compare that with pre-trained statistics, so they can see the deviation of the statistics between the real-time and the training data, and alert if there is an inaccuracy or a drift in the model, and so on. Another thing that they do, they write back all the production data as a new feature set in the feature store. So when we want to do retraining, we just do retrain and create a new, deploy the model into production in like a canary deployment and continue to run. So it's like all those very, very hard problems that your IT and DevOps and ML engineers do manually could be automated using some of those frameworks. Okay. And this is, by the way, snapshots of monitoring the models, the skew between production and data. It also supports Grafana dashboards. You can attach it to Grafana dashboard to see like per model statistics, deep dives, real-time serving data, and so on. So before I'm diving into the next example, so let's understand the application that I'm going to demonstrate. So we have, let's see, okay, so I'll show this demo, but there's also another demo I may show. It's essentially the same. This one is a real application running in one of the hospitals for real-time patient deterioration analysis. So think about, you have a bunch of patients in ICU, and you want to know which one deserves immediate care, what is the prediction around, what kind of treatment they need to have, and other types of predictions. So we need to combine 3 different data sets. We need to combine real-time data from the real-time bed sensors, heart rates, movement detectors, and other essentials. We need to combine it with data from operational systems, like the blood sample results from yesterday, and so on. And maybe static data like the patient gender, age, medical history, and so on. So we may need to have different tools that bring data from different operational systems, some in batch, some in real time. We want to feed all of that data into the feature store. Once it's in the feature store, we want to run interactive exploration on that to evaluate our features. When we feel it's sort of great, we build the feature vectors and run an automated machine learning pipeline the way that we did it before. Grab data directly from the feature store, run AutoML, do deployment or testing of the model, and then deploy the production model. The production model works against the feature store to grab real-time features from the feature store and combine them with the user requests. And there's also all the telemetry we mentioned for model monitoring that writes back the results into the feature store, so we can do post-production analysis of what happens in production. So this is how a real application pipeline looks like, with data gathering, with exploration, with automated training pipelines, with microservices for serving and for automated monitoring and post-analysis. So this entire project I can show you in 3 different notebooks. By the way, it's also covered in the memorandum documentation. There are a few examples. There's a stock analysis example with like stock data, and there's this example I was just covering with the hospital patient deterioration data. So you can just go through those notebooks later on. Maybe someone from our team can just throw those into the Slack, so you can see those. Okay, so let me open. So I'll show a different example, but it's relatively similar. It's an example I showed earlier today. This one is more of a mobile application churn prediction. So think about, you have mobile users that each one of them has like a transaction feed. Is playing games, is logging into the application or logging out, etc. It may have other data sets like he just paid some credits, is logging into another application. It may have some other data like social data, is doing a like or a share on some things. And we want to know, based on all of that activity, is this customer is likely to churn? Why do we want to know that early? Because then we can throw in some incentives. If it's a gain, then some free credits and coins and so on. If we can also anticipate the lifetime value of a user, we can make sure that we spread those coins to the right people and not necessarily the guys that are going to waste it. So we can invest in those guys that may bring us more value. By the way, this kind of application kit, we work with few of the gaming or application companies, and that increased their top line by a few percent in terms of revenue. That's introducing this kind of a pipeline. So the machine learning, if you apply it to real production applications, it could have a huge impact on the business of those companies. I think it maybe even more than 10% of fresh revenue, because they apply this type of algorithms to their business applications. Okay, so let's understand how we build all that pipeline. So the first thing, we're going to grab some data. This is the sample data for, that's a fraud application, sorry. So we're going to grab some data. It's based on some Kaggle project of fraud information. And these are transactions of actual, people buying stuff with their credit cards. And each one has like categories and amounts and different metadata. So this is just the data. Now we want to build some pipeline that will take that data. We'll run some sort of data extraction functions, like what is the hour in the day of week, and so on. And may want to do some aggregations. We want to essentially say, I want to bucket the transactions to an hourly average or hourly sum. How much did you spend in the last hour or the last day, and so on. So I need to build aggregations and other data extractions. So we build an ingestion pipeline, and this ingestion pipeline, we can just ingest the data and plot the data. So you can see that after we do that ingestion, this is how the data looks like. So The system automatically created aggregations. You see those aggregates. It automatically added columns for hour and day, see hour and day of week automatically. And so these are things you can do in your pandas as well. But the nice thing about it, this pipeline can be saved and run in production on a Kafka stream or on an HTTP endpoint or on a CSV files. Again, the same implementation could work in for almost any scenario. The next thing that we want to build is take another data set of the event activities, like the user did log in, log out, changes personal details. Those type of changes have a lot of indication around fraud. Someone that logs in a lot, potentially may have some indication, or changes passwords, etc. May have indications on potential fraud. So we want to build another feature engineering pipeline. So this time we want to do one-hot encoding, because we want to take this event string and convert it to like one-hot encoded data. So again, just creating graphs and do one-hot encoding and ingest the data. So now the ingested data or the pipeline will just have, you see, one-hot encoding. Another thing that we want in fraud is to also group things by categories. Let's assume you're buying shoes or you're buying food. It's not the same. You buy food all the time. I don't know a lot of people that buy shoes all the time, besides my wife. But it's like if you see someone buying shoes every day, then it's probably an anomaly. Then this is why we want to group the purchases, the transactions based on some categories. So we built another engineering pipeline that does value mapping, encoding, build aggregates on those categories, etc. So then we could make sure that someone is not buying shoes again over and over. And maybe there are, by the way, categories that are more risky, that tend to be more fraudulent than others. So in this case, you see that we built things that usually, if you go and take developers and tell them go write it in Spark or in a production pipeline, what I'm showing you now here will probably be a matter of a few months of work. And especially writing SQL code and all of that, it doesn't perform, and it takes a lot of time to debug and work with. So here, through very simple object orientation, we created those pipelines, we visualize them. By the way, as we create the pipelines, we can just go here into that project. We go to the feature store. Everything that we did in our notebook is always connected to the system. We don't have to work with the notebook. We can go into the transactions, see the features that we generated. You see it auto-learn the features. These are the transformations that we've defined. This is a preview of the data that we have. This is the statistical behavior of each one of the features. And we're going to use that statistical analysis later on for the model monitoring. Okay, so here I can essentially ingest all the data. By the way, one very important feature set is the labels. So we can also generate the label data from the transactions. We can create sort of a special column that says, yeah, fraud or not fraud, based on some indications from the transaction data. So here we created another feature set or another feature for the label data. So now we've created all the data sets. By the way, we can now build multiple applications based on those features, not just one. We mentioned before, maybe we could do a lifetime value application or a churn application, all running from the same data. So now, as we've created the features, we want to build a feature vector and train based on that feature vector. So building a feature vector is relatively simple. We give it a name. We call out all the features that we want. So features from the transaction log, features from the event, essentially all of them, features from the parties, and also we want to say that this feature is the label column for the training. So as we assemble this feature vector, there's essentially going to be a processing engine that takes this definition and it does a very intelligent join across all of those features. Why do we need intelligent joins? Because every such feature may have a different time dimension, and we need to stitch them together in something called the time traveling mechanism. So transactions from today get joined with events from today and not with events from yesterday, and so on. Google time traveling for feature stores, and see more details on that. Anyway, we created a feature vector. We can save it. As we save it, it immediately goes into the UI and so on. And now we can just get the offline features. Essentially, I gave you a feature vector. Now give me the feature vector, and you see that all those features that we created from all the different feature set are going to be correctly joined into a full training set that we can just now go and use for training. You see all the columns and so on. Now we want to run training, so we use what we've seen before is the ML run capabilities for automatic doing auto ML. Is we can just take a function and we can just import a function from a marketplace. We don't even need to write our training classification function. It's an AutoML function, so we provide a list of algorithms we may want to run, etc., into the training, and we just run the training job. We run the training job, we get all the results, all the accuracy. Again, if I go into that project, I can see the training job. I can see the different results for the different algorithms. I can see the output artifacts for the training and so on. And you see, so I don't do almost anything on my notebook, but you see everything gets recorded, and I could go back and forth with the versions and the artifacts and so on. So I ran the training. Now I have a model with all the statistics that I need. And now let's go and do some serving. So in order to do the serving, so we can take an off-the-shelf serving function. We don't need to write it, but in this case, we want to show a slightly more sophisticated serving function. What's sophisticated about this serving function beyond and the serving function, there's a notion of there's like a serving class that you need to implement or reuse from what the system comes with. And those serving classes have a load and a predict hooks. So the load loads the model, and the predict essentially predicts, throws some data and returns the prediction results. But here we wanted to do some more computation, because in reality we get sometimes we get bad data in production as well. So in this case, in this application, we get null values for some fields. We want to substitute the null values in the fields with the statistical information from the feature store. So we want to replace the null value with the mean value of the same feature that is stored in the feature store, with sort of the average value. So this way we get an accurate model. In some cases, maybe replaced with some default categories. So we added a pre-processing phase into our serving function just to deal with imputing and some other manipulations of the data. Essentially, our pre-processing does a feature service get, which means that I'm going to give you the key of the user. You give me a feature vector based on that, and then do the prediction. In order to turn this class of Python into some real-time function, again, not a lot of work, go to function with the serving engine, and that's it. I'm going to have I have a microservice for real-time function. Now, this function, I want to give it multiple models and an ensemble. I don't want to serve a single model like the trivial way. I want to create an ensemble. Ensemble is essentially something that goes and does infer on all the three models and sort of selects the average value. So this way, if one model misbehaves, the other models may sort of correct the first model and create a better average. Okay, so we create the function. We tell it we need a voting ensemble routing mechanism, and we just add the three models that we generated, the random forest, gradient boosting, and other boost into the ensemble. Again, 2 lines of code, and you have real-time pipeline with ensemble and multiple types of models. And now we want to test that pipeline. Okay, so if we go and build it into containers, etc., then going and testing, that's a nightmare. So why not do the testing on a simulator within our notebook? So when you do 2 mock servers, essentially creates a virtual pipeline inside your in-memory of the notebook, so you can feed it with events and you get the response of the pipeline as if it was really running in production. So we're creating a mock server, and you can see we can also see that we can just throw into the feature vector some key and get back the full vector that we've defined. So every time we change the user ID, we're going to get a full feature vector, and we feed that feature vector into the model, and this way we know if we had the fraud or not. If we want to test the entire model endpoint, we can just tell it which endpoint we want to test, give it some sample ID, and then see the result of the model. Essentially, this one is not fraudulent, which is great. Now, if we want to deploy this pipeline that we've defined into full production cluster, either the local cluster or even a remote cluster or multiple clusters, we just do deploy. And you see that this deploy is actually creating containers and deploying that on the Kubernetes cluster. And essentially, it returns back with an HTTP endpoint, which is used for serving. And we can also test against that HTTP endpoint. So what you've seen in those 3 notebooks, something that usually takes a few months of work for a lot of people, how we can essentially build ingestion pipelines from operational databases, from streaming data from HTTP, run training without doing too much feature engineering, just by selecting our features from sort of a catalog, running exploration, running training, using different algorithms, and then building sophisticated model serving pipeline with ensembles and multiple models and feature enrichment, all in 3 simple notebooks. So with that, let me go back into the presentation. So we've seen again how we did all those different steps of ingestion from different sources. Again, you can find, if you go into the MLRun project space, you'll find a lot more information about each of those items, about the feature store, about the serving pipelines. Again, there are multiple examples, also examples with real-time NLP pipeline, which is really cool. You know, taking like PDF documents, breaking 2 paragraphs, turning it, doing entity extraction and enrichment. Again, many different examples that are very sophisticated but the general idea is that we make things simple. Maybe it's slightly harder for the data scientists to get used to building it this way, but once you've done it, then your production is already automated. What you've done in development is ready for production without a lot of extra ML engineering work. Okay, so again, everything is here. Maybe one last thing I can show you. We talked about the model monitoring part. So we have our 3 models with the different algorithms, and we could just go and see their progress, their predictions, their drift. All that again is done automatically. I could dive into a specific model. This one is sort of like the iris data, so you can see the individual features, the behavior of those features in production versus expected. I can actually see the real values of every feature in every point in time, because everything goes into like a time series, a high performance time series database that tracks the behavior of the features over time. Okay, so with that, let's go back into the presentation. We've seen this sort of entire pipeline, and so just to summarize, there's also right now an MLOps for Good hackathon that we're running together with a bunch of companies, Microsoft, MongoDB, ODSC is one of the community partners, and other organizations. You know, we have judges which are sort of leading practitioners in the industry, and so anyone that wants to join, just we can update you on the Slack, and you could just go into the hackathon page very recommend. It's really more. It's not really about creating a new algorithm. It's really more how to operationalize an idea that you have, which is serving for good cause. If you want to listen more about MLOps and operationalizing machine learning, we have sort of a bi-weekly or tri-weekly webinar with a lot of industry leaders from different companies. Every session we're speaking about different topics, and you can also watch the recordings for each one of the topics that we've covered.